Every star, every planet, every atom dances to the rhythm of an invisible force. We can't see it, but it sculpts everything, from the birth of galaxies to the beating of a compass needle. If this unseen thread vanished, the universe would collapse into chaos. This is magnetism, the universe's hidden architect, the silent sculptor of existence. For centuries, we misunderstood it. We saw lightning, auroras, and compasses, but never realized that magnetism threads the entire cosmos. From the smallest electrons to intergalactic space, magnetic fields weave the fabric of everything. But before we journey deeper into the story, there's something important to understand. This documentary is not fiction, nor is it fully generated by artificial intelligence. Every concept and event you'll encounter is based on verified, peer-reviewed science, carefully examined and interpreted for clarity. Some of the visuals you'll see are artistically generated to help illustrate complex ideas that exist beyond the range of human vision. Think of them not as imagination, but as visualization, a bridge between what science understands and what we are still discovering. And if you find value in these explorations, thoughtful science told with care, a quick subscribe helps us continue creating more journeys like this one, because the universe has many stories to tell, and magnetism is just the beginning. Now, let's follow this invisible architect from the birth of stars to the edge of the observable universe, because without magnetism, the cosmos as we know it would never have formed. The planets that nurture life, the stars that forge elements, the galaxies that spiral in cosmic ballet, all depend on invisible lines of force that science is only beginning to map. We'll discover that magnetism isn't just a curiosity of physics. It may be the language the universe uses to write its own story. Magnetism permeates everything, from the iron core of our planet to the vast halos of galaxies stretching across hundreds of millions of light-years. And yet, for most of human history, it remained invisible, misunderstood, or completely ignored. We thought magnetism was a local curiosity, a trick of lodestones and lightning, confined to Earth and perhaps the solar system. Only recently did we discover that this same force operates across cosmic distances, shaping the largest structures in existence. The story begins with William Gilbert's revolutionary insight in 1600, but it took 3 more centuries to understand its implications. In the 1800s, Michael Faraday visualized magnetic lines of force, invisible threads that could be mapped using iron filings sprinkled around magnets. What Faraday discovered in his laboratory, modern astronomers now observe stretching between galaxies. The first hints of cosmic magnetism emerged in the early 20th century, when astronomers noticed that light from distant stars was sometimes polarized, twisted in ways that suggested it had passed through magnetic fields. But the scale remained unimaginable until radio astronomy matured in the 1950s and 1960s. Radio telescopes revealed something extraordinary: synchrotron radiation pouring from the space between galaxies. This phenomenon occurs when high-energy electrons spiral along magnetic field lines, creating a distinctive radio signature. The intensity of this radiation told astronomers that magnetic fields existed not just around individual stars or galaxies, but throughout intergalactic space. The breakthrough came through Faraday rotation measurements, a technique that measures how magnetic fields twist polarized radio waves as they travel across cosmic distances. By analyzing this twisting effect in radio signals from distant galaxies, astronomers began mapping the magnetic scaffolding of the universe itself. What they discovered defied every expectation. The universe isn't just matter and empty space, it's threaded by magnetic fields like a vast circulatory system. These cosmic magnetic highways span scales from the subatomic to the intergalactic, creating a hierarchy of organization that scientists are still struggling to understand. At the smallest scales, individual atoms generate tiny magnetic fields through the spin and orbital motion of their electrons. Step up to planetary scales, and we find magnetic fields generated by circulating currents in molten metallic cores. Earth's magnetosphere extends 65,000 kilometers into space, far beyond the orbit of most satellites. Stellar magnetism dwarfs planetary ones by factors of thousands. Our Sun's magnetic field reaches beyond Pluto, creating the heliosphere, a magnetic bubble that shields the entire solar system from the worst cosmic radiation. When solar magnetic field lines tangle and reconnect, they unleash the energy equivalent of billions of nuclear weapons in events called solar flares. But even stellar magnetism pales beside galactic fields. The Milky Way's magnetic field threads through 100,000 light-years of space, organizing the motion of cosmic rays and channeling the flow of interstellar gas. Radio observations from telescopes like the Very Large Array, VLA, and the Low Frequency Array, LOAR, reveal magnetic field lines that spiral along our galaxy's arms, creating elegant patterns visible across hundreds of thousands of light-years. And beyond galaxies lies something even more remarkable. The cosmic web itself appears to be magnetized. Modern radio surveys detect magnetic fields threading the filaments of dark matter and gas that connect galaxy clusters across hundreds of millions of light-years. These intergalactic magnetic fields are incredibly weak, millions of times fainter than Earth's field, but their scale is so vast that they may contain more total magnetic energy than all the stars and galaxies combined. Recent observations from LOFAR and the Australian Square Kilometre Array Pathfinder, ASCAP, have mapped these cosmic magnetic highways in unprecedented detail. They reveal a universe where magnetic fields act as invisible rivers, channeling matter and energy along preferred pathways. Without these guiding fields, the cosmic web might collapse into chaos. The profound realization is this: gravity alone cannot explain the intricate architecture of the universe. While gravity provides the foundation, the scaffolding that holds galaxy clusters together, magnetism provides the blueprint. It determines where stars form, how galaxies rotate, and even how matter flows along the cosmic web's filamentary structure. Think of magnetic fields as the universe's bloodstream, carrying not just energy but information across cosmic distances. Changes in magnetic field strength or direction can trigger star formation in distant molecular clouds, influence the paths of cosmic rays traveling between galaxies, and even affect the rate at which supermassive black holes consume matter. This invisible architecture operates through several key mechanisms. Magnetic pressure, the force exerted by compressed magnetic field lines, can support gas clouds against gravitational collapse, or, conversely, channel matter along field lines to create the filamentary structures we observe throughout the cosmos. Magnetic reconnection events, where field lines break and reform, release enormous amounts of energy that drive some of the most violent phenomena in the universe. Perhaps most remarkably, magnetic fields possess memory. Unlike gravitational or electromagnetic radiation, which diminish rapidly with distance, magnetic fields can maintain their structure across cosmic time. The magnetic field threading our galaxy today may preserve information about conditions that existed billions of years ago, when the Milky Way was still forming. As we peer deeper into space with next-generation radio telescopes, we're discovering that magnetism may be the universe's longest-lasting signature, an invisible archive of cosmic history written in field lines that span the observable universe. The cosmic thread isn't just a metaphor, it's a physical reality, connecting everything from the quantum vacuum to the largest structures ever detected. And we're only beginning to read what it says. Every star begins its life in a magnetic cradle, and without that invisible embrace, the cosmos would be a cold, dark place. The story starts in molecular clouds, vast regions of gas and dust that drift through interstellar space like cosmic fog. These clouds can span hundreds of light years and contain enough material to birth thousands of stars. But there's a puzzle. If gravity were the only force at work, these clouds should collapse and form stars much faster than we observe. Something must be slowing the process, regulating star formation with exquisite precision. That something is magnetism. Molecular clouds are threaded by magnetic field lines that act like invisible scaffolding, providing structural support against gravitational collapse. This phenomenon, called magnetic pressure, creates a delicate balance. Too much magnetic support, and star formation stalls completely. Too little, and gravity overwhelms the system, leading to chaotic runaway collapse. The Zeeman effect, the splitting of spectral lines in the presence of magnetic fields, allows astronomers to measure magnetic field strengths in these distant nurseries. Observations from radio telescopes reveal field strengths of about 10 to 100 microgauss in typical molecular clouds, roughly comparable to Earth's magnetic field, but distributed across vastly larger volumes. When gravitational forces finally overcome magnetic support, the collapse doesn't happen uniformly. Instead, matter flows along magnetic field lines, like water through invisible channels. This channeled flow creates the flattened, rotating disks we observe around newly forming stars, protoplanetary disks where planets will eventually coalesce. But magnetism doesn't just guide the formation of stellar disks, it actively shapes their evolution through a process called magnetic braking. As material in the disk tries to spiral inward toward the growing protostar, magnetic field lines act like invisible tethers, transferring angular momentum outward and regulating the rate of accretion. Without this magnetic regulation, matter would plunge into protostars so rapidly that they would become unstable and potentially explode before nuclear fusion could begin. The Atacama Large Millimeter Array, ALMA, has revolutionized our understanding of this process by imaging protoplanetary disks in unprecedented detail. These observations reveal intricate spiral patterns, gaps, and rings, structures that can only be explained by the complex interplay between gravity, gas pressure, and magnetic forces. The beautiful spiral arms visible in these young systems aren't random. They're magnetic field lines made visible by the dust and gas that flow along them. As planets form within these magnetized disks, they inherit the magnetic architecture of their birth environment. Rocky planets like Earth can develop their own magnetic fields if they possess molten circulating metallic cores. Gas giants may retain some of the magnetic flux from their formation disks, creating the complex magnetospheres we observe around Jupiter and Saturn. But the influence of magnetism extends far beyond individual stellar systems. On galactic scales, magnetic fields orchestrate some of the most magnificent structures in the universe, spiral galaxies. For decades, astronomers puzzled over spiral arms. Mathematical models showed that rigid spiral patterns should wind up and disappear within a few 100 million years due to differential rotation, the fact that stars closer to the galactic center orbit faster than those at the periphery. Yet spiral galaxies like our own, Milky Way, have maintained their elegant structure for billions of years. The solution lies in galactic dynamo theory, the idea that rotating, conducting fluids can generate and amplify magnetic fields. In galaxies, this conducting fluid is ionized gas that flows between the stars. As the galaxy rotates, this gas stretches and twists magnetic field lines, converting rotational energy into magnetic energy through a complex process that astronomers call the alpha-omega dynamo. The result is a galactic magnetic field that threads through the spiral arms, providing the organizational structure that keeps them coherent over cosmic time. Radio observations from the Very Large Array reveal that magnetic field lines in spiral galaxies align beautifully with the visible spiral arms, creating a cosmic blueprint that guides star formation and galactic evolution. Our own Milky Way exemplifies this magnetic architecture. Radio polarization measurements show that our galaxy's magnetic field follows the spiral arm structure, with field strengths of about 5 microgauss in the galactic disk. These fields channel cosmic rays, high-energy particles that would otherwise escape the galaxy, keeping them trapped within the galactic disk, where they can influence star formation and gas heating. The magnetic structure also explains why spiral galaxies don't fly apart despite their rapid rotation. While dark matter provides the gravitational foundation that holds galaxies together, magnetic fields provide additional structural support, particularly in the outer regions where dark matter density is lower. Perhaps the most stunning example of galactic magnetism is the Whirlpool Galaxy, M51, located about 23 million light-years away. Radio observations reveal magnetic field lines that trace the galaxy's spiral arms with breathtaking precision, creating a pattern that looks almost like a cosmic fingerprint. The field lines follow the arms so closely that astronomers can use magnetic field maps to predict where new star formation will occur. Interactions between galaxies can dramatically reshape their magnetic fields. When M51 encounters its smaller companion galaxy, NGC 5194, the gravitational interaction stretches and amplifies magnetic field lines, triggering waves of star formation that propagate along the spiral arms like cosmic tsunamis. Recent observations from ALMA and the VLA have revealed even more intricate details. In some galaxies, magnetic fields create bar-like structures that funnel gas toward the central regions, feeding supermassive black holes and triggering periods of intense star formation. In others, magnetic winds launched from the galactic center help regulate star formation by removing gas and preventing runaway stellar birth. The elegance of this system is remarkable. Magnetism acts as both architect and conductor, designing the structure of galaxies and orchestrating their evolution over billions of years. From the moment a molecular cloud begins to collapse under its own gravity, to the grand spiral patterns that define mature galaxies, magnetic fields provide the invisible framework that transforms chaos into cosmic beauty. And without magnetism, galaxies would be shapeless clouds of stars, and stellar nurseries would be sites of violent, uncontrolled collapse. Instead, we live in a universe where invisible fields create order from disorder, guiding the formation of the very stars that make life possible. And as we'll discover, this magnetic guidance extends to protecting the worlds where life can flourish. 40,000 kilometers above your head, an invisible battle rages every second of every day. The sun hurls a stream of charged particles, the solar wind, toward Earth at speeds of up to 800 kilometers per second. If this cosmic hurricane reached our planet's surface, it would strip away our atmosphere, sterilize the surface, and render Earth as barren as Mars. What protects us is a magnetic shield, Earth's magnetosphere, that deflects this deadly stream and preserves the delicate atmospheric cocoon that makes life possible. The magnetosphere is one of the most elegant structures in the solar system, a teardrop-shaped bubble of magnetic force that extends from Earth's core to well beyond the orbit of the Moon. On the day side, where it faces the solar wind head-on, the magnetosphere compresses to about 65,000 kilometers from Earth's center, roughly 10 times our planet's radius. On the night side, it stretches into a long tail that extends millions of kilometers into space. This protective barrier exists because Earth possesses something that most planets lack: a strong, stable magnetic field generated by circulating currents of molten iron in our planet's outer core. The mechanism, called the geodynamo, operates like a cosmic dynamo, converting the energy of Earth's rotation and internal heat into magnetic energy that radiates outward through the planet and into space. The magnetosphere's structure is breathtakingly complex. Nested within it are the Van Allen radiation belts, donut-shaped regions discovered by physicist James Van Allen in 1958, where the magnetic field traps high-energy particles like an invisible cage. These belts serve as a kind of early warning system, capturing dangerous particles before they can reach the lower atmosphere. When the solar wind encounters Earth's magnetic field, something remarkable happens: magnetic reconnection. Field lines from the Sun's magnetic field connect with Earth's field lines in a process that releases enormous amounts of energy. This energy powers some of the most beautiful phenomena on our planet: the auroras. Auroras occur when charged particles, channeled along magnetic field lines, collide with atoms in Earth's upper atmosphere. Oxygen atoms emit green and red light, while nitrogen produces blue and purple hues. The result is a natural light show that follows the precise geometry of Earth's magnetic field, creating oval patterns centered on the magnetic poles. But auroras are more than just cosmic beauty. They're visible evidence of our magnetic shield at work. During intense geomagnetic storms, when the sun unleashes particularly powerful bursts of charged particles, auroras can be seen as far south as the Caribbean, indicating that our magnetic protection is being severely tested. The most famous historical example occurred on September 1, 1859, when astronomer Richard Carrington observed a brilliant solar flare, the first recorded observation of such an event. The resulting geomagnetic storm was so intense that auroras appeared over Rome, Hawaii, and the Caribbean. Telegraph systems worldwide failed or sparked, and some operators received electric shocks. In our modern electronically dependent civilization, a similar event could cause trillions of dollars in damage and take years to recover from. Space weather prediction has become crucial for protecting satellites, power grids, and astronauts. Organizations like NOAA's Space Weather Prediction Center monitor solar activity and issue warnings when dangerous geomagnetic storms are approaching. The magnetosphere, far from being a passive shield, actively responds to changing solar conditions, sometimes weakening dangerously during intense storms. To understand the magnetosphere's importance, we need only look at our planetary neighbors. Mars, roughly half the size of Earth, lacks a global magnetic field. NASA's MAVEN mission has directly measured how the solar wind strips away the Martian atmosphere at a rate of about 100 grams per second. Over geological time, this process has transformed Mars from a warm, wet world with a thick atmosphere into the cold, dry planet we see today. Venus presents a different case study. Despite being nearly identical to Earth in size, Venus has no significant magnetic field. Its thick atmosphere provides some protection through its sheer mass, but the upper layers are constantly being eroded by the solar wind. Without magnetic protection, even Venus-like atmospheric pressure isn't enough to guarantee long-term stability. These examples highlight a crucial factor in planetary habitability. Magnetic fields may be just as important as liquid water for sustaining life over geological timescales. This realization has transformed how astronomers search for potentially habitable exoplanets. Detecting magnetic fields around distant planets remains one of the greatest challenges in exoplanet science. Current methods are indirect. Astronomers look for radio emissions generated by charged particles interacting with planetary magnetic fields, or study how stellar winds interact with exoplanetary atmospheres. The TRAPPIST-1 system, with its 7 Earth-sized planets orbiting a red dwarf star, provides a fascinating natural laboratory. Red dwarf stars are known for producing intense stellar flares and strong stellar winds. For any of the TRAPPIST-1 planets to maintain atmospheres capable of supporting life, they would likely need robust magnetic fields. Observations with radio telescopes like LOFAR are beginning to probe these distant magnetospheres. Proxima Centauri b, the nearest potentially habitable exoplanet, faces similar challenges. Its host star, Proxima Centauri, is an active red dwarf star that regularly unleashes powerful flares. Whether Proxima b possesses a magnetic field strong enough to protect a potential atmosphere remains unknown, but answering this question is crucial for assessing the planet's habitability. Future missions are being designed specifically to detect exoplanetary magnetic fields. The ARA&A Space Telescope will study exoplanet atmospheres in unprecedented detail, looking for signatures of magnetic protection in atmospheric composition and retention. Ground-based radio arrays, like the Square Kilometre Array, will have the sensitivity to detect radio emissions from exoplanetary magnetospheres around nearby stars. The techniques being developed may even allow astronomers to study the magnetic fields of potentially habitable moons. Jupiter's moon Europa and Saturn's moon Enceladus both harbor subsurface oceans beneath icy crusts. These moons exist within their parent planet's powerful magnetospheres, which provide some protection from cosmic radiation, but they also generate their own weak magnetic fields through interactions between their oceans and their planet's magnetic environments. Understanding planetary magnetic fields has implications beyond habitability. Some researchers propose that magnetic fields could be artificially generated to terraform planets like Mars. Theoretical concepts include placing magnetic dipoles at Mars's L1 Lagrange point to create an artificial magnetosphere, potentially allowing atmospheric pressure to rebuild over geological timescales. The deeper we probe into magnetic protection, the more we realize that magnetospheres aren't just shields, they're life support systems. They preserve atmospheres, regulate space weather, and create the stable environments where complex chemistry can evolve over billions of years. Earth's magnetic field has another profound implication. It may have been essential for the origin of life itself. Some theories suggest that magnetic field reversals and fluctuations could have provided energy sources for early biochemical reactions, while magnetic protection allowed complex organic molecules to survive cosmic radiation bombardment. As we search for life beyond Earth, we're learning that the universe's invisible architecture plays a crucial role in determining where life can emerge and flourish. Magnetism isn't just a physical force, it's a cosmic guardian, creating safe havens where the extraordinary complexity of life can unfold. But this protective influence extends beyond individual planets to cosmic scales, where magnetic fields guide and trap some of the universe's most energetic particles. In 1912, Austrian physicist Victor Hess ascended 5,300 meters in a hydrogen balloon, carrying primitive radiation detectors into the thin upper atmosphere. What he discovered changed our understanding of the universe forever. High-energy radiation was pouring down from space, penetrating Earth's atmosphere with energies that dwarfed anything humans could produce. These cosmic rays, misnamed because they're actually particles, not electromagnetic radiation, represent some of the most energetic phenomena in the known universe. The most powerful cosmic ray ever detected, observed by the Pierre-Auger Observatory in 2007, carried the energy of a baseball thrown at 100 kilometers per hour, all concentrated in a single atomic nucleus. What makes cosmic rays truly mysterious isn't just their incredible energies, but how they travel through space. Without magnetic fields to guide and contain them, these particles would stream out of galaxies in straight lines, disappearing into the cosmic void. Instead, magnetic fields turn galaxies into cosmic particle accelerators and prisons, trapping and recycling high-energy particles for millions of years. The story begins in the most violent environments the universe can create: supernova explosions. When massive stars reach the end of their lives, they detonate with energies that briefly outshine entire galaxies. The shock waves from these explosions, racing through space at thousands of kilometers per second, become cosmic particle accelerators through a process called Fermi acceleration. As the shock wave encounters cosmic rays, magnetic fields on both sides of the shock wave bounce particles back and forth like cosmic ping-pong balls, accelerating them to higher and higher energies with each collision. This process can continue for thousands of years, eventually producing particles with energies billions of times greater than anything achievable in human-built accelerators. But here's where magnetism becomes crucial. Without galactic magnetic fields, these accelerated particles would escape into intergalactic space within a few million years. Instead, the Milky Way's magnetic field acts like an invisible maze, deflecting cosmic ray paths and keeping them trapped within the galactic disk for 10 to 20 million years. Radio observations reveal this cosmic ray population through synchrotron radiation, the characteristic glow produced when high-energy electrons spiral along magnetic field lines. This radiation maps the magnetic structure of our galaxy with exquisite precision, showing how cosmic rays trace invisible magnetic highways that thread through interstellar space. The cosmic ray energy spectrum tells a remarkable story. At lower energies, the spectrum follows a smooth power law, indicating a galactic origin. But at the highest energies, about 10 to the 19th electron volts, the spectrum steepens dramatically in what's known as the GZK cutoff, named after physicists Kenneth Greeson, Georgy Zatsepin, and Vadim Kuzmin, who predicted it. The GZK cutoff occurs because ultra-high-energy cosmic rays interact with photons from the cosmic microwave background, losing energy as they travel cosmological distances. This means the most energetic cosmic rays must originate relatively nearby, within about 150 million light-years of Earth. But identifying these sources remains one of astronomy's greatest unsolved mysteries. Candidates include active galactic nuclei powered by supermassive black holes, gamma-ray bursts from colliding neutron stars, and even more exotic possibilities like the decay of super-heavy dark matter particles. The Pierre-Auger Observatory and the telescope array in Utah continuously monitor the sky for these ultra-high-energy events, trying to trace them back to their sources. What makes this detective work so challenging is that magnetic fields deflect cosmic ray paths like invisible lenses, scrambling directional information. A cosmic ray that appears to come from the constellation Orion might actually originate from a source in Sagittarius, its path bent by magnetic fields it encountered during its million-year journey through the galaxy. This brings us to an even deeper mystery: the origin of cosmic magnetic fields themselves. How did the universe become magnetized in the first place? Two competing theories attempt to explain cosmic magnetism. The astrophysical scenario suggests that magnetic fields were generated by the first stars and galaxies, then amplified and spread by galactic winds and merger events over cosmic time. The primordial scenario proposes that magnetic fields were created in the very early universe, perhaps during inflation, phase transitions, or the formation of the first structures. Recent observations of intergalactic magnetic fields support elements of both theories. LOFAR and other radio arrays have detected magnetic fields with strengths around 1 femtogauss in the space between galaxy clusters. Fields so weak they contain only a few magnetic field lines per cubic meter, yet they span hundreds of millions of light years. These intergalactic fields may hold clues to some of the universe's deepest mysteries, including the nature of dark matter. Some theoretical models propose that axions, hypothetical particles that could constitute dark matter, convert into photons in the presence of magnetic fields. If this process occurs, it could create observable signatures in the cosmic microwave background or in light from distant galaxies. The connection between magnetism and dark matter runs even deeper. Computer simulations of cosmic structure formation show that dark matter filaments, the scaffolding along which galaxies form, could generate magnetic fields through charge separation as they collapse under gravity. Conversely, magnetic pressure could influence how dark matter clumps, affecting the rate and pattern of galaxy formation. Some researchers speculate that dark matter particles themselves might be magnetic, interacting through forces beyond the standard model of particle physics. If confirmed, this could explain both the large-scale distribution of dark matter and the ubiquity of cosmic magnetic fields. Cosmic ray ionisotropy provides another window into these mysteries. While cosmic rays appear to arrive from all directions fairly uniformly, sensitive detectors reveal subtle patterns, slight excesses from certain directions that may point toward their sources or reveal the large-scale structure of galactic magnetic fields. The Ice Cube Neutrino Observatory, buried under Antarctic ice, has detected complementary evidence. High-energy neutrinos, ghostly particles that interact only weakly with matter, arrive at Earth carrying information about cosmic ray acceleration sites. Unlike cosmic rays, neutrinos travel in straight lines, undeflected by magnetic fields, providing direct pointers to the universe's most violent environments. As we develop more sensitive instruments, we're beginning to see cosmic rays and magnetic fields as part of a single, interconnected system. Magnetic fields shape cosmic ray propagation, while cosmic rays trace magnetic field structure, creating a cosmic feedback loop that influences everything from star formation to galactic evolution. This realization has profound implications for understanding how energy and information flow through the universe. Cosmic rays carry not just energy, but chemical elements forged in stellar cores and distributed by supernova explosions. Magnetic fields guide this cosmic recycling, ensuring that heavy elements essential for planet formation and life are mixed throughout galactic disks rather than remaining concentrated in stellar graveyards. Perhaps most remarkably, the same magnetic fields that trap cosmic rays in our galaxy may be connected to the vast magnetic networks that thread the cosmic web. If so, our local cosmic ray population might be influenced by magnetic field configurations that span hundreds of millions of light years, making every cosmic ray that strikes Earth's atmosphere a messenger from the largest structures in the universe. We stand at the threshold of a revolution in cosmic understanding. Across the globe, a new generation of radio telescopes is coming online with the power to map magnetic fields across the entire observable universe, revealing the invisible architecture that connects everything from quantum particles to cosmic superclusters. The square-kilometer array, when completed, will be humanity's most sensitive radio telescope, capable of detecting magnetic field signatures from galaxies so distant their light began traveling toward us when the universe was barely 1 billion years old. This cosmic archaeology will reveal how magnetism evolved alongside the first stars and galaxies, potentially solving the mystery of how the universe became magnetized. Already, Pathfinder instruments like ASCAP and LOFAR are transforming our understanding. ASCAP's POSSUM survey is creating the most detailed map of cosmic magnetism ever attempted, measuring Faraday rotation in over 1 million distant galaxies to trace magnetic field structures across billions of light years. These Faraday rotation measurements work like cosmic CT scans, building three-dimensional maps of magnetic fields by analyzing how polarized radio waves are twisted during their journey through magnetic plasma. Each measurement provides a line of sight through the cosmic web, and combining millions of such lines creates a detailed picture of the universe's magnetic skeleton. What emerges from these observations is breathtaking. A universe woven together by magnetic threads that span the largest structures ever detected. The cosmic web isn't just a gravitational phenomenon, it's electromagnetically active, with magnetic fields that may regulate the flow of matter between galaxies and influence the formation of new structures across cosmic time. LOFAR has made particularly striking discoveries at low radio frequencies, where magnetic field signatures are strongest. Its observations reveal magnetic fields threading through galaxy cluster halos, connecting individual galaxies to their neighbors across millions of light years. These fields may help explain how galaxy clusters evolve and why they contain such precisely organized arrangements of galaxies. The implications extend far beyond pure astronomy. Understanding cosmic magnetism is driving breakthroughs in fusion energy research, where scientists are trying to contain plasma temperatures of 100 million degrees using magnetic bottles similar to those that confine cosmic rays in supernova remnants. Tokamak reactors like ITER use twisted magnetic field configurations called stellarators to prevent hot plasma from touching reactor walls. The magnetic field geometries required for successful fusion are surprisingly similar to those observed in astrophysical jets launched by black holes and neutron stars, suggesting that nature has already solved many of the engineering challenges we're struggling with. Some fusion researchers study solar magnetic reconnaissance events to understand how magnetic energy can be rapidly converted into particle acceleration and heating. The sun's corona routinely demonstrates magnetic confinement and energy release on scales far beyond human technology, providing a natural laboratory for testing fusion concepts. Magnetism is also inspiring revolutionary concepts for space travel. Magnetic sail propulsion could use spacecraft-generated magnetic fields to interact with the solar wind, enabling efficient interplanetary and eventually interstellar travel without carrying fuel. The same magnetic fields that protect Earth could become highways for human expansion into the cosmos. But perhaps the most profound discoveries involve magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. These cosmic lighthouses generate magnetic fields so intense they distort the quantum vacuum itself, creating conditions that exist nowhere else in the observable universe. Magnetar bursts release more energy in milliseconds than our Sun produces in months, powered entirely by magnetic field reconfiguration. Studying these events helps physicists understand how matter behaves under the most extreme conditions possible, testing fundamental theories about the nature of space and time. Fast radio bursts, mysterious millisecond duration signals that arrive from distant galaxies, show distinctive polarization patterns that suggest they pass through regions of intense magnetic activity. Some FRBs appear to originate from magnetars, but others remain unexplained, possibly involving magnetic phenomena we haven't yet discovered. The polarization of FRB signals acts like a cosmic probe, sampling magnetic fields throughout the universe. As these brief signals travel from their sources to Earth, they encounter magnetic fields in their host galaxies, in intergalactic space, and in our own galaxy, accumulating polarization signatures that create a record of every magnetic environment they pass through. These observations are leading to profound philosophical questions about the universe's fundamental nature. Some researchers propose that magnetic fields aren't just organizing principles for matter and energy, they may be how the universe stores and processes information. Consider this: magnetic fields have memory. Unlike gravitational waves or light, which dissipate rapidly, magnetic field configurations can persist for billions of years, maintaining their structure across cosmic time. The magnetic field threading our galaxy today may contain information about conditions that existed when the Milky Way was first forming. This has led to speculative but fascinating theories about cosmic consciousness and information processing. If magnetic fields can store information across cosmic scales and time, could the universe itself be a kind of information processing system, with magnetic fields serving as its memory banks and communication networks? The idea isn't as far-fetched as it might seem. Modern theories of quantum gravity suggest that information is a fundamental aspect of reality, as important as matter and energy. Magnetic fields, with their ability to organize matter, store energy, and persist across vast scales, could be nature's way of preserving and processing cosmic information. Some researchers speculate about magnetic field networks that could support complex information processing across galactic scales. Vast, slow-thinking systems that operate on timescales of millions or billions of years. While purely speculative, such ideas highlight how magnetism might play roles in cosmic evolution that we're only beginning to imagine. As our instruments become more sensitive, we're discovering that magnetic fields exhibit structure and behavior that seems almost purposeful. They channel matter along preferred pathways, trigger star formation at precisely the right rates to maintain galactic stability, and create the protective environments where life can emerge and flourish. The Square Kilometre Array will probe even deeper mysteries. It will map magnetic fields in the cosmic dawn, when the first stars were born. It will trace magnetic evolution through cosmic history, and it will test whether magnetic fields played a role in seeding the large-scale structure that makes galaxies, stars, and ultimately life possible. We're also beginning to recognize that understanding cosmic magnetism may be essential for humanity's long-term survival. Climate change, asteroid impacts, and supervolcanic eruptions are terrestrial threats, but the most existential risks may come from space, Gamma-ray bursts, supernovae, or solar events that could overwhelm Earth's magnetic defenses. Learning to predict and potentially influence magnetic field behavior could help us protect our technological civilization from space weather and cosmic catastrophes. Some visionary concepts involve using controlled magnetic fields to deflect asteroid impacts or even to shield entire planets from radiation during nearby supernova explosions. As we push toward becoming a spacefaring species, magnetic field technology may prove as important as rockets and life support systems. Magnetic shields could protect Mars colonies from radiation. Magnetic energy storage could power interstellar voyages, and magnetic field manipulation might eventually allow us to terraform worlds or even construct artificial habitats in space. But beyond practical applications lies a deeper truth. Magnetism may be the universe's fundamental organizing principle, the invisible thread that weaves matter, energy, space, and time into the cosmic tapestry we observe. Understanding this thread doesn't just advance science, it reveals our place in a universe far more interconnected and purposeful than we ever imagined. We began this journey by following a simple compass needle, its magnetic tip pointing faithfully north. We end it contemplating invisible threads that connect the quantum realm to the cosmic web, threads that may carry not just energy and matter, but memory itself across the vast expanse of space and time. Magnetism, we've discovered, isn't merely a force, it's the universe's way of creating order from chaos, of building structure from randomness, of preserving information across epochs that dwarf human history. From the moment the first atoms formed in the cosmic dawn to the birth of stars that forged the elements of life, magnetic fields have guided, protected, and organized cosmic evolution with a precision that still astonishes scientists. The magnetic shield that protects our world, the invisible scaffolding that shapes galaxies, the cosmic highways that guide matter between the largest structures in existence, all are manifestations of a single universal principle that operates across scales we can barely comprehend. Perhaps most profoundly, we're beginning to understand that magnetism may be how the universe remembers. While stars burn out and galaxies collide, magnetic fields persist, carrying information about cosmic conditions that existed billions of years ago. They may be the universe's longest-lasting signature, an invisible archive of everything that has ever happened since the first magnetic fields emerged from the quantum foam of the early cosmos. As our instruments become more sensitive and our understanding deeper, we're recognizing that we live in a universe far more interconnected than previous generations could have imagined. The same force that guides migrating birds and powers our technology threads through the cosmic web, connecting every atom to every galaxy in a vast network of invisible influence. Standing beneath the night sky, we can now envision the true cosmic architecture, magnetic field lines stretching between stars, wrapping around planets, threading through galaxies, and extending into the deepest voids of intergalactic space. We are not isolated observers in an empty universe, but participants in a cosmic symphony conducted by forces we can feel but cannot see. Perhaps the universe isn't just matter and light, but memory flowing endlessly along invisible lines of force. The cosmic thread is real. It connects everything to everything else, and we are just beginning to learn how to read the story it tells.